Hi everybody, it's Ajanette, and I'm going to go over your chapter 6 lecture, which introduces the concept of probability. Now, this will be interesting. I usually bring in a bag of Starburst, and I have everybody pull a handful of Starburst for this particular lecture. And I don't have that additional hands-on, mechanism to help it stick. So hopefully I can use some explanations that'll help it stick, and you can visually go along with me, okay? So I'm going to start by sharing my screen, and I'm going to go to our chapter 6 lecture. And let me go ahead and launch this. I'm probably not going to reference the whiteboard too much during this, but we'll see if we can get through it conceptually. So first of all, let's talk about what probability is. So when we're looking at probability, you've already really been introduced to the concept when we talked about z-scores and the normal distribution. Remember I said that 70% of the population falls within one standard deviation of the mean. In other words, the probability that you're going to pull a score that falls within one standard deviation is probably a 70% chance, right? Or I said the 95% of the population falls within 2 standard deviations. So if you randomly pull someone, there's a 95% chance that they're going to fall within 2 standard deviations. So pretty much probability is definitely related to the z-score, but it's looking at probability, proportions, they all kind of go hand in hand. But probability is what's the likeliness of a specific event or occurrence in the context of research. What's the probability that their score will fall in a certain location on the normal distribution chart? The higher the probability, the more certain we are, right? So if there's a 95% chance, then we're more confident in that than if there's a 5% chance. So it's more likely they're not going to be in the critical region, and that's what we're testing as researchers. Are they in the critical region? And the probability is so low that when they are in the critical region, it's usually because our independent variable or our treatment had some sort of effect, okay? So we need to know kind of what's happening in the overall population to determine like what's the predictable probability or likeliness in the corresponding sample. And that probability, right? So if I know there's a certain makeup in the population, then I can predict as I'm sampling what the makeup's going to be in my corresponding sample. So when you talk about probability, if you think of a jar of marbles, if you've ever seen, like, guess how many jelly beans are in this jar, for instance. If I'm calculating, or if I'm trying to estimate the probability of an occurrence in a jar of marbles, and there's 50 black and 50 white marbles, then if I'm going to pull out a marble, I pretty much have a 50% chance it's going to be black, and I have a 50% chance that it's going to be white. So let's say the marbles, or the jar has 90 black marbles and only 10 white marbles. Well, when I go to pull a marble, there's a 90% chance it's going to be black, and only a 10% chance it's going to be white. Why? Because I know the makeup of the jar itself. So my sampling probability is going to be predicated upon what the makeup of the population is, right? And so when I talk about probability, probability is the connection from our population to our sample. So based on the structure of our population, probability lets us kind of predict what the structure is going to be of our sample. But when we're talking about inferential statistics, we're doing the exact opposite. We don't know quite often what behaviors or patterns are occurring in the population. So what we do is study samples and make inferences about the population based on what we're seeing in the sample. So probability is that bridge that inferential statistics gets to rest on in order to reliably draw conclusions about the population based on sample data. Does that make sense? So we'll see how that pans out a little bit more. When we're talking about mathematical notation, we notate probability by P, or sometimes we'll say probability of A, probability of B, right? But we also notate it as P. So when we're talking about the definition or formula of probability, then what we do is we look at the total number of possible options, or the total number of desired options divided by the total number of possible options altogether. And so if I could get you to think about a deck of cards, right? A deck of cards, I think there are 52 cards actually. 13, there's 52 cards. So I need to correct this. So there's 52 cards, 13 of each set, right? There's from a 2 all the way to an ace. So that is actually 52 cards, 13 cards in each suit. And so 26 red cards, 26 black cards for a total of 52 cards, okay? So if I say, what's the probability of selecting an ace? I know there's 4 aces because there's 4 different suits, right? There's hearts, clubs, diamonds, and hearts, clubs, diamonds, and spades, right? So there's 4 different suits. Each one has 13 cards. There's one of each, so there's an ace of spades, an ace of hearts, an ace of diamonds, and an ace of clubs. So what's the probability of selecting an ace? Well, there's a total of 4 aces, and the total number of cards is 52. So if we go back to this formula, the total number of outcomes, so I'm saying, what's the probability of an ace, okay? The number of possible classified as aces, so that's 4, divided by the total number of cards altogether, 52. So our probability of selecting an ace is going to be 4 out of 52. The probability of selecting a queen of hearts, again, if I go back, there's only 1 queen of hearts in the deck, right? But a total of 52 cards. So that would be 1 in 52. So we end up getting 4 in 52 for drawing an ace, because there's 4 possible aces and 52 possible cards altogether. And for B, we get a queen of hearts. There's only 1 of those. So it's 1 possible pull for queen of hearts and 52 altogether. Now, what I can do quite often when I'm talking about probabilities is I can talk about them in proportions, which is fractional, or I can talk about them in percentages. And in order to get a percentage, we just divide that fraction. So we divide the numerator by the denominator, and then we times 100, and that gives us the percentage. So I can convert 4 of 52 to 4 divided by 52 equals 0.076. I would times that times 100. It's going to round up to 7.6% or 8%, okay? So I have an 8% chance of pulling an ace. And then a 1 in 52 chance of pulling that queen of hearts. Divide 1 by 52, it's 0.019, which is 1.9%, round up, that's 2%, right? So I have a 2% chance of pulling a specific queen of hearts. Make sense? Okay. So when we talk about probability, now it's really interesting when you're talking about pulling these cards, right? Let's say I'm pulling the ace first, right? And then now when I go to pull the queen of spades, now there's not 52 cards, there's only 51 cards, right? So keep that in mind. We talk about simple random sampling, and simple random sampling is when everybody in the population has an equal chance of being selected. So there's not anything, I'm not showing any kind of bias, or I'm not limiting or restricting who I'm sampling. I'm just anybody in the population I can potentially just randomly pull in my study. There's also independent random sampling. So if you're selecting more than one person, then it's really important that the probabilities are staying the same with each selection, right? And so this actually assumes if I pull the first card, they have a 1 in 52 chance of being selected. But if I don't put that first card back, now the second pull only has a 1 in 51 card chance of being selected. So, because the number of cards is reducing, that would violate this independent random sampling rule, because what it's assuming is that I'm replacing that card back and that they are maintaining the same probability, that each person I pull has a probability of being pulled again. So you're throwing them back into the jar so they can be pulled again. Does that make sense? I hope so. So that being said, you have, this is essentially at the top here is without replacement, and then this is with replacement. So I'm assuming that that probability, that denominator score stays constant, and I'm putting the card back on my second draw, putting it back on my third draw. So technically, I can potentially pull an ace again in my second draw, even if I already pulled it in the first, okay? So it doesn't change, that probability does not change from one person to the next. So I'm gonna go ahead and let you do a learning check. Just go ahead and pause me, read through these questions, and then restart me when you're ready. But be sure to work these out so that you can kind of let this stuff marinate a little bit, work through, rumble with it so that it's starting to get those wheels moving and making sense, okay? Okay, so let's assume you started me back up. So let's read it. A survey of the students in a psychology class revealed there were 19 females and 8 males. Of the 19 females, 4 had no brothers and sisters, and 3 of the males were also the only child of the household. If a student is selected from the class, A, what's the probability of obtaining a male? So first of all, I need to know how many people in total. So the psychology class had a total of 19 plus 8, 27 people, right? But then I need to know what's the probability of obtaining a male. Well, there were 8 males in total. So the probability is 8 out of 27. Now you can also divide that and actually get a percentage, and that's fine too. What's the probability of selecting a student that has at least 1 brother or sister? That should say 1 brother or sister. So I know that of the 19 females, 4 had no brothers and sisters. And of the males, of the males were also the only child, 3 of the males. So there were a total of 7 with no brothers and sisters, right? So a total of 27 minus the 7, so 20 were remaining that actually had brothers and sisters. So the probability of selecting a student that had brothers and sisters was 20 over 27, or you can calculate the percentage. What's the probability of selecting a female with no sister? So of the 19 females, I'm focused on females with no sister, and 4 had no brothers or sisters. So it would be 4, because that's the only possible outcome, divided by 27, okay? Now let's go down to number 2, looking at a jar of marbles with 10 red and 30 blue. If we randomly select 1 marble, what's the probability of obtaining a red? So there's a total of 10 red, so that's going to be our numerator, and 40 marbles altogether. So it's a 25% chance. If you take a random sample of n equals 3 from the jar, and the first 2 are both blue, okay? What's the probability of the 3rd marble being red? Now remember, this is a little tricky. If you actually were reducing the denominator, then you weren't considering with replacement, right? You were thinking of simple random sampling rather than just random sampling. And in random sampling, we're always going to put it back. So that's 10 out of 40. That's a 25% chance. Okay? So let's talk a little bit about the normal distribution. Some of this will be review because in chapter 5, we already talked about some rules and patterns that we see with a normal distribution. And remember, I drew it out for you and I showed you that each chunk represents a certain portion or probability. So remember, it's symmetrical. So whatever proportion of the population which is in one slice on the right side of the mean, it also is equal on the left side of the mean as well. So that distance between the mean and the first standard deviation is 34.13%. That's the proportion of the population that actually scores between the mean and one standard deviation. That means on the other side, it would be 34.13%. So whatever you see happening on the right side, you also see happening on the left side because it's a symmetrical distribution, okay? And remember, the z-scores tell us the exact location of any given score in a data set. So because we can precisely pinpoint a probability of a specific location on that z distribution, each z-score has a corresponding probability. What is the probability of pulling that z-score? So the probability, because we said about 95% of data falls within 2 standard deviations. So we know that 95% of the scores fall between a -2 z-score and a +2 z-score. So the probability of pulling any score between those two barriers is 95%. We move those barriers in to 1 standard deviation, we know that that's about 70%. When we looked at those precise numbers, that ended up being 68.26%, falling between -1 and 1. And then what's the probability of falling between the mean and 1? 34.13%. So each z-score corresponds to a specific probability of pulling that score. Think of that normal distribution as a pie, and we're cutting it into pieces. And each of those pieces represents a proportion of the overall pie. The overall pie is 100%. And depending upon what segment you're talking about, it represents a larger percentage of the pie, okay? We know that those specific patterns are always existent, where the mean is 0, standard deviation is 1, and so for the piece of the pie between 0 and 1, it's 34.13%. Then for the piece of the pie between 1 and 2, it's 13.59%. If I add those two things together, which I kind of need my calculator for that, so give me a second. If I add those two things together, hold on, because it's slowing down a little bit. So I'm going to pull up my calculator. And if I add those two things together, that's 34.13% plus 13.59%. So this distance from 0 to 2 represents 47.72% of our data. Remember that this whole side of the pie is an equal 50% because this is the median, right? It's the point at which 50% falls on the right and 50% falls on the left. So I know if I just take 50 minus the 47.72, that only, that only leaves 2.28% left of the 50% of the pie. And notice above a 2 z-score is 2.28% of the population. Now I can further divide that 2.28% down into between 2 and 3 2 and 3 z-scores, or 3 and 4 z-scores, or 4 and 5. So I can break this down into incremental parts. So this area can always be broken down into incremental parts. You have a z-score of 0.10, 0.20, 0.30, 0.40, and there's a specific probability that corresponds to each of those z-scores. Thankfully, we don't have to figure that out, because some mathematician that loves this crap and you know, didn't have anything better to do figured it out for us. So I'm going to introduce you to the unit normal table in just a second. Now keep in mind, whatever we see happening on the right side is also happening on the left side. So 34.13% is between the mean and 1 standard deviation above the mean. It's also the same over here below the mean. So 34.13, 13.59, and 2.28. You add them all together, it's 100%. Make sense? Perfect. So here's a breakdown of it with both sides, and we can see how it also corresponds to the z-scores, right? This is saying 0 is our mean, right? So a z-score of 0 where there's 0 standard deviations, or 1 z-score with 1 standard deviation above the mean, so on and so forth. Notice on this chart, it's breaking that down. Instead of lumping all this together for just greater than 2 or lower than -2, it's breaking it down, and it's giving you the exact distance between 2 and 3 and 3 and 4, okay? Now, I want you to notice that if we look at the pie starting over here, your percentage is increasing. So you have about a 1% chance, less than 1% chance, 0.1% chance of being at -3 z-score. And then your chance increases now to 2.3%. So in other words, this actually means that 2.3% of the population fall between -4 z-score and -2. And then if I go all the way up to 15.9, 15.9% of the population, or I have a probability of 15.9% of being -1 standard deviation or lower. And then it goes up, I have a 50% probability of being lower than the mean. I have an 84.1% probability of being 1 standard deviation or below. So 1 standard deviation above the mean or lower. I have a 97.7% probability of being 97.7% of the population, that's not saying I have a probability, 97.7% of the population is accounted for if we look at everybody up to a z-score of 2 and below. So if I were to score here, I'm in the 97.7 percentile. If I were to score here, I'm in the 99.9 percentile. Makes sense? Meaning that if you flip it, I had less than a 1% chance because 99.9% of the population doesn't get scores that high. Make sense? So this down here tells you what percentage of the population scores up to that point, and you can flip it to say it's the percentile, and then, you know, it's, if you score here, you're in the 50th percentile. If you score here, you're in the 2.3% percentile. Or you can flip it and say, what's the probability of me getting this score, okay? Okay. So let's talk about probability and the normal distribution curve. I've already alluded to the fact that z-scores absolutely follow that normal distribution, and we actually have a chart and a tool. So I'm going to go to our course, and it's in modules, and it's going to be under Appendix B tables. And what I'm introducing you to right now, it's also in your book, it is our unit normal table. Our unit normal table looks at the normal distribution like a piece of pie, and what it does is it tells us what percentage of the total population is accounted for in the piece of pie that corresponds to that z-score. And there's 3 different columns, each, well, there's 4 actually. A represents the z-score itself. Remember I told you, we're talking about z-scores in chunks right now. 1, 2, 3, -1, -2, -3. But they can be broken down into incremental parts, okay? They're continuous. So you can have a z-score of 0.10, 0.20, 0.30, okay? So this actually breaks them down into hundredths. And you can see how they're getting bigger? So this is the z-score. And I want to introduce you to something, a conception called the body and the tail. The body is the larger portion and the tail is the smaller portion. So when I'm looking at a z-score, let's say a z-score of 0, I know that's going to be right in the middle. So that makes it hard to say what side's the body and what side's the tail. Let's look at a z-score of 1, because that's a familiar number to us, okay? A z-score of 1 has an 84.13% in the body and only 0.158% in the tail. The body's always the bigger portion and the tail is always the smaller portion, okay? So if I were to do this, and let's say this is a z-score of 1, right? And here's a z-score of 1. This would be the body, it's the bigger portion. So if you draw a line, like I am cutting the pie right here at that z-score boundary, okay? Then the bigger piece of the pie is the body, and the smaller piece of the pie is the tail. And these columns tell you what percentage of the pie is in the body and what percentage of the pie is in the tail. And when you add those 2 numbers together, they're telling you 100% of the pie. So if I look at 1 and I cut the pie right at a z-score of 1, then 84.13% of the pie is in the body and 1.1587 is in the tail. And again, if I end up adding those 2 things, 0.8413 plus 0.1587, it equals 1, 100% of the pie, okay? So the columns B and C together total 100% of the pie. I also have column D here that tells me the distance, what percentage of the pie is between the mean and the z-score. So in our case, our z-score was 1. It's telling us that if I'm just looking at the precise halfway midpoint of the pie, that mean, the amount of pie between the exact middle and the z-score of 1 is going to be 34.13%. Okay, does that make sense? And sometimes that's helpful because if I want to find out, you know, sometimes I want to find out what's the probability of scoring between 1 and the mean, and that would tell me. Or sometimes I might want to use this to mathematically, you know, subtract some stuff to figure out what's left over. There's going to be different questions at the end of this chapter asking you to look up z-scores or calculate the probability of getting a certain z-score. And so all of these columns will be useful, and you have to be able to differentiate between the body, the tail, and the distance between the mean and the z-score, and kind of recognize what the question's asking. Is it asking me the percentage in the body? Is it asking me the percentage in the tail? Is somehow using the segment useful in this solution? So you got to really think about what it's asking you. I almost always draw out a normal distribution, and I draw a line and I mark where that z is. So I can visually determine where's the body, where's the tail, and then that helps me answer the questions. So hopefully this tool and resource will be helpful for you, but you're going to use it a lot in this chapter, okay? And so let me go back to our lecture now. Okay. And I just need, us, oops, wrong one. I need Zoom to kind of get comfortable with the PowerPoint again. Okay, so So everybody gets, it's 100% of the pie. It's broken down into different slices, and this is the probabilities that correspond. Okay, so now when I'm talking about the normal distribution, you know, I'm telling you that unit normal table, somebody mathematically figured this shit out, and I love it. I love it that they love math enough to do that. I got better things to do with my time, so I love that I can just go to the chart. There's going to be a chart for every single statistic, every technique that we use, and so you'll be thankful that those mathematicians did that work too. So because we know these properties exist with normal distributions, we can then use the z-distribution to help us determine those probabilities. So now a z-score can actually help us as an inferential tool, okay? Assuming we have a mean of 500 and a standard deviation of 100, then we know a z-score of 1 is going to be equal to a score of 600. A z-score of 2 is going to be equal to a score of 700. And we can now actually look at what's the probability of pulling that z-score, or what proportion of the population scores in that range, okay? And so here you can kind of look at this question, and it can translate into a proportion question, saying what proportion of the scores are greater than 700. We can kind of conceptualize it as percentages, proportions. It really doesn't matter. They're the same. Proportions translate into percentages, and percentages can be translated back into proportions, okay? When we're talking about this particular question, is asking us what percentage of scores on a normal distribution are greater than 700. So it's basically asking us, if we calculate the z-score that corresponds to 700, that's going to be 2, right? So the first thing we have to do is conceptually figure out what's it asking us. Then we have to calculate the z-score that corresponds to the score of interest. Then we're going to have to draw a line exactly where we want it to be. I like to draw, sketch out the thing. So I'm going to say a mean of 500, standard deviation of 100, and it's asking me about the probability of getting a raw score of 700. And I'm going to now just conceptualize it as a z-score. So I want to just take you through what I'm going to do before I move to the chart. You can pause and try to figure it out on your own, and then restart when you're ready. But I do want to take you to the whiteboard, and I want to show you what this all looks like, okay? So first of all, it's giving me, I'm working with a normal distribution, and it gave me a mean of 500. Here's 1 standard deviation, 2 standard deviations, right? I know my standard deviation was 100. So I know this score right here is going to be 600. This one's going to be 700. This one's going to be 400. And this one's going to be 3. And if I do my z-scores, I know that it's always going to start with 0. 1 standard deviation above is 1. 2, -1, -2. Okay? And where it's having me focus is it's asking me about what's the probability assuming a z-score of 700. So that's where I want to draw my line, right? Now it's really important to be able to identify what's the body and what's the tail, okay? What we know is the larger portion is the body, and the smaller portion is the tail, okay? We know that. So if you shade all of this, it's asking me what percentage is greater than 700. So it's basically asking us what percentage is here in the tail. What percentage of scores are in the tail? I can go back to my unit normal table, and I can look up a z-score of 2, because that's the z-score that corresponded. And if you look here on the very first line, that's a z-score of 2. 97.72% of the data is in the body, which would be the bigger part up to the z-score of 2. And then 2.28% is in the tail, okay? So if I translate that back to our drawing here, then 2.28% is in the tail. Make sense? Okay, so let's go back to our lecture and see if we can walk you through. Okay. So the steps involved, the first thing I'm going to do is I'm going to figure out what it's asking me. It's asking me what's the probability that X is greater than 700 or X is greater than a z-score of 2. So the first thing I have to do is I'm translating it to proportion, what proportion of scores correspond to greater than 700. I'm going to calculate a z-score for that 700, right? So I drew a picture for step 2 and I'm identifying what portion of the body, or excuse me, what portion of the distribution is it asking me about? It's asking me about over here, the little tail. I'm going to calculate my z-score and that gives me 2. So it's asking me the probability of scores falling above a 2. And then when I look at that specific unit normal table that we just looked at, your answer is 2.27%. Make sense? Okay. You tried to do it on your own. Hopefully we matched up. If not, dig in and look at the individual steps and where you are off, okay? So that unit normal table is really, really important. I want you to really kind of work with it, familiarize yourself with it. Let me know if you have any questions. There are a couple of things I want you to be mindful of in that unit normal table. We have a modified version of the unit normal table. So we don't actually see all of the possible z-scores. We have a missing chunk, okay? And also when you look at the unit normal distribution, looking at the table, I also want you to see it's only positive numbers, okay? So keep in mind that everything that happens on the right side, because it's symmetrical, also happens on the left side. So if there's only a 2.28% probability of finding, of a score falling above a positive 2, then there's only a 2.28% of it being less than a negative 2 as well. Remember, whatever's happening in this tail is also happening in that tail. So keep that in mind, it's symmetrical. And then also keep in mind that we don't necessarily have all the potential scores, okay? This is a modified or condensed version, okay? Okay, so I'm gonna go back now to your lecture. And here's a couple learning checks for you. I really recommend that you shut down the video and pause. You might even want to go take a break for a minute, come back and let your brain settle in, and then come back and say, okay, let me put all this together. Let me make some sense of it. And try to work these out on your own. I love to draw out my graphs, so that helps me a lot. Hopefully that's a tool that can help you a lot too, but I'm going to encourage you to just pause, try to work through these learning checks and figure it out, okay? Okay, assuming that you are now ready to come back and you're refreshed and ready to look at these answers, let's talk a little bit, okay? So what proportion of the normal distribution corresponds to a z-score with values greater than z equals 1? Okay, so we're looking at greater than z equals 1. So I'm going to go back to my whiteboard and I'm going to clear this. I'm going to change my color back to black, okay? And, oh, didn't clear it. Okay, And now I'm looking at my mean, right? And then it's asking me a z-score of 1, so I know it's just 1 standard deviation. And it's asking me greater than a z-score of 1. So what it's asking me for is this area right here, right? Greater than. So this is the bigger piece of the pie, and this is the littler. So this would be the tail, and this would be the body, okay? So then now I'm gonna go to my unit normal table, and I'm gonna look for a z-score of 1, and I'm looking for the percentage in the tail, which is 15.87%, okay? Do you see that? So let me go back. And here we are. And there it is, 15.87%, okay? Now, what's the probability of a z-score less than now, 1.5, okay? And it's asking me, yeah, less than 1.5. So again, I'm gonna go back. I'm gonna go to my whiteboard. I'm gonna clear this one, and I'm gonna draw my new table. And here's my distribution, here's my mean, here's 1 standard deviation, here's 2, here's -1, here's -2. It's asking me for 1.5. So 1.5 is going to be right in the middle of 1 and 1 and 2. So here's 1.5, and it's asking me less than, okay? If I go this way, that's greater than. If I go this way, it's less than. So it's asking me what percentage of scores are here. Is that the body or the tail? The bigger piece is the body, and the smaller piece is the tail. Okay, and so it's asking me what percentage of scores are in the body. So then I'm going to go to my unit normal table, and I'm going to look up a z-score of 1.5, which is right here in the top, right here, and the portion in the body is 93.32%. 93.32%. So let me go back. Here we go, 93.32%. So a lot of this is just drawing out your chart and figuring out where you got your answers. So now let's look at this last one. A score less than -0.50. Okay, so let's go back to our whiteboard, and let's clear this guy out. And now I'm going to draw a new one. Oops. And it's asking me, here's my mean, right? And it's focused on this side now. So this would be 1, 2, this is -1, this is -2. It's asking me for -0.5. So -0.5 is going to be below the mean because it's negative, and it's halfway. It's only a half a standard deviation. So it's going to be halfway between -1 and -2, okay? So now it's asking me for the scores less than. That would be to the left is less than, and this way would be greater than 0.5, right? Because we're going negative, more negative to be less than 0.5. So it's asking me this portion right here, okay? Which is the tail. Remember, the smaller part is the tail, and the bigger piece of the pie is the body, okay? And so now I'm going to look at my unit normal table, and I'm going to ask what probability of scores occur in the tail at 0.50. And remember, it doesn't give me negatives, but it does give me whatever's happening on one side of the mean is also happening on the other because it's symmetrical. So I'm going to look up for a z-score of 0.5, in the tail, it's 30.85%, okay? So let's go back to our presentation. And it's 30.85%, okay? So you're gonna have lots of homework questions that are gonna get you to play with that table. And what it's really helping you to understand is it's helping you, number one, to really get comfortable with z-scores, really get comfortable understanding the shape of the normal distribution and how probability kind of intersects with that normal distribution, and how z-scores are layered right on top of that, and how we have a predictable percentage of the population that corresponds to z-scores. So it's really getting you comfortable with those foundational concepts that are critical for inferential statistics, okay? So I know it can be frustrating and stressful and you're like, what the hell do I need this for? It really is laying a really strong foundational understanding and knowledge base for inferential statistics, okay? Now, I also want you to be mindful that that fourth column, the part between the mean and the standard deviation, or excuse me, the first z-score, that is an important part when we're having to like figure things out, when we need to understand pieces. And so it might ask you the middle 60%. So I'm gonna look up 30%, recognizing that there's also another 30% on the other side. So that between the mean and the z-score can be used to figure that stuff out. What if I want to understand the probability of someone scoring between this value and this value? That middle, that fourth column will be important. Excuse me. So if I'm talking about this practice question, for a normal distribution, what z-score values form the boundaries that separate the middle 60% from the rest of the scores, okay? So let's look at this. I want you to keep in mind there's two really important lessons here. First, we're not only learning how to use that fourth column, but we're also recognizing that not only can you look at the probability that corresponds to a z-score, but you can also look up the z-score that corresponds to a probability. The table can be used to go both ways, okay? So let's first start by drawing our normal distribution, okay? And it's asking us, what are the boundaries of the 60%, okay? So we're looking for 30% here and 30% here. So what is the z-score that corresponds to those boundaries, right? So what we can do is we can look up in the chart, right? We can look up column C and say, what column C has 30%? Because that tells me the z boundary. That will tell me the z that corresponds to the portion here between the mean and the standard deviation that equals 30%. So let's look that up using our unit normal table. And we're going to focus on our z here, right? And we're going to now be looking at which of these z's has 30%. And if you look here, right, this is about where we start to get 30%. Now, this is 30.23%. This is 29.95%. So we have to make a judgment call. Are we going to say z-score is a 0.84 or 0.85? I might err on this side and say 0.84. So if I go back here, remember, it's only telling me positive numbers, but I know that whatever's over here on the right side also corresponds to the left side, only it's a negative. So the boundaries that correspond to the middle 60% are 0.8, anything between negative 0.85 z-score and positive 0.85 z-score. And I do want you to consider something. just to double check a logic, right? We know about 70% of the data falls between a -1 and a +1 z-score. Remember, about 70% of your data falls within 1 standard deviation above or below. So this is reasonable that about 60% would be about 0.85. That's reasonable. So you can also do like a logic check based on what you know, okay? So let's go back to our lecture. And we have about 0.85%, okay? That's the Z boundary. Z equals 0.85. It's gonna fall between -0.85 and +0.85. Those are our boundaries, okay? So that's how that third column could be helpful. So let's do a couple practices, again, to familiarize ourselves and to look at other theoretical questions that we might be asking, okay? First, just getting you comfortable looking at percentages that correspond to z-scores, figuring out is it the body or is it the tail? And then secondly, I'm using a little bit of logic and having to conceptualize what's happening. So go ahead and pause, play with these yourself, and then when you're ready, then go ahead and hit play and we'll restart. Okay, so we're gonna go into this learning check, and I'm looking at z equals less than 0.25, greater than 0.80, less than -1.5, and greater than -0.75, okay? So me personally, my first step is always, I'm gonna go to my, my drawings, okay? So I'm gonna clear my drawings, and I'm just gonna go ahead and divide us into 4 so we can do them all at once. And here I am looking at 0, 1, 2, -1, -2. And this one is asking me less than 0.25, okay? So 0.25 is gonna be a quarter of the way between 0 and 1. So it's gonna be right about here, okay? 0.25 z-score. And it's asking me less than, so that's gonna go backwards on the number line, right? So it's gonna be this portion right here, which is gonna be, it's bigger than this portion on the right, so it's gonna be the body. And I'm gonna go ahead and I'm gonna go to my unit normal table, and I'm gonna look up the probability in the body for 0.25. Doesn't matter if it's negative, right? It's still, hold on, sorry, I just messed up because it's actually asking me for a positive, and I think I was just focused on a negative. So let me go back. I was. So this is all wrong. It's actually asking me for a positive 0.25, not negative 0.25. So let me fix that. Okay. Okay, so here we go. I'm going to divide it into 4s. And I'm going to say this is going to be 0, 1, 2, -1, -2. Sorry, those should be dashes. And then it's actually asking me right here, not negative. So it's 0.25, okay? So if I draw my line, it's right, oops, ooh, that was interesting. It's right, oh, that's interesting. I don't know how I'm doing that. Okay, so just ignore me for a second. It's right here. Oh, shit. So, okay. I don't exactly know how it skipped down. So I'm gonna close it out and start over. Okay, it's still lower, and I don't exactly know how I got there. Yeah, I have no clue. So we'll figure that out later. That being said, I'm looking here at my 0.25, right? No, not you. Technology is a beautiful thing and a bad thing all at once. So 0.25, right? And it's asking me for less than 0.25, so it's over here. And that would be, because that side's bigger, that's going to be the body. And over here is going to be the tail. And so I need to go to my unit normal table, and I need to look at 0.25, and I need to look at the proportion in the body, and that's going to be 59.87%. So 59.87%, okay? Now my next one, I'm gonna go and I'm gonna look at greater than 0.80%. So let me draw my normal distribution. And here's my 0, here's my 1, here's my 2, -1, -2. And you're going to have your 0.80% is not quite at the 1 yet. So I'm going to go ahead and draw my line right about here. That's 0.80. And it's asking me greater than 0.80. So it's looking to be this way for greater than. So that's the smaller piece of the pie. So it's the tail. So now I'm gonna find the percentage that corresponds to greater than 0.8%. And that's going to be the proportion in the tail is 21.19%. And that's 21.19%. Okay, so let's just go back and check those numbers. 59.87, 21.19. And there we go, okay? And so I'll let you do the next two on your own. Now let's go to the other and we'll look at number 2. For a normal distribution, find the z-score location that divides the distribution as follows. So now I'm looking at boundaries, what separates the top 20% from the rest. And so it's looking at the top 20%. So let's go ahead, and it's asking me for the z-score that does that. So I'm going to go ahead and clear this. And okay, so let me go ahead and go to my drawing tools again. And what the hell was it asking me again? Anybody remember? Because I don't remember now. The top 20% from the rest. Okay. So the top 20%, I'm going to do a drawing and I'm going to look at the top 20%, where 20%'s here and 80%'s here. So this is the tail. I can look up either the proportion in the tail that corresponds to 20%, or I can look up the proportion of the body that corresponds to 80%. Both are going to take me to the same z-score. So here I'm going to go look at my unit normal table, and here we go, the proportion in the tail. I'm focused on that at 20%. It looks like I'm going to be right here at 0.85 or 0.84. See that? Notice 80%, a little over in the body, and 0.19%, 77 in the tail. So I'm going to stick with 0.85. Someone might want to choose 0.84. Kind of subjective there. And so let's go back. And there you go. Okay. separate the top 60% from the rest. And so when I do that on my drawing, I'm going to have it wants me to look at drawing at about 60%, 40%, right? So it's saying 60%, the top, oops, damn. Here we go. 60%, the top 60%, okay? That means there's 60% in the body and 40% in the tail. So I'm gonna look up in my unit normal table and find the one that shows 40% in the tail, which will also lead me to 60% in the body. So it looks like 40% in the tail is going to be right here between 0.26 and 0.25 z-score. And that also corresponds to the 60% in the body. And here we go. Okay. Now we're talking about separating the middle 70%. This is important that I show you this. So when we talk about the middle 70%, right, we're talking about where I have 70% in the middle, which would mean I have 30% left over. So I have 15% here and 15% here. Remember, it's a normal distribution, so our mean goes right down the middle. So I'm going to have 35% here and 35% here. So I can do it a couple of ways. I can look at the boundary with 15% in the tail, right? I can do that. Or I can focus on looking at the portion that has 35% between the mean and the z-score. Either way, it doesn't matter. I'm looking for these z-scores, okay? So I'm gonna go to 15% in the tail is easier, but notice I'm focusing on that middle 70%. So I'm going to go to my unit normal table, and I'm going to look at my 15% in the tail. And that's going to be right here between 103 and 1.04. Okay. And so going back to, here we go. So hopefully that helps. Lots and lots and lots of practice. Don't get too frustrated with yourself, okay? Okay, so as I mentioned, not only can we use the unit normal table to help us figure out the percentage that corresponds to a z-score, we can also use it to help us figure out a z-score that corresponds to a percentage. But then at the same time, because we know z-scores can be tied back to x values, we can also find the percentage that corresponds to any x value as well. So we can actually say what's the probability of getting a certain score within our data set. And so what we do is we first translate that into a z-score, and then we look up the percentage that corresponds to that z-score, and the percentage that corresponds to the z-score also corresponds to the raw score, okay? So for IQ scores, looking at what's the probability of getting 120 IQ, and then as we've already talked about, I'm going to go ahead and go to my whiteboard. As we've already talked about, the distribution for IQ is 100 mean with a 15 standard deviation. So that makes this 115, that makes this 130, 85, and 70. And it's asking me about 120, which this would be 120, 125, and then 130, right? So it's asking me right here, right? About 120. And as I don't remember, we'll have to go back, but it's asking me about a z-score, IQX of 120. So I need to figure out what the z-score is. So my Z formula is X minus the mean divided by the standard deviation. So in this case, it's going to be 120 minus 100 divided by, 15. So 5 divided by 15. And is that right? X, it was 120, I believe, minus our mean of 100 divided by a 15 Z-score. So 5 divided by 15. Oh, damn, I closed it. I'm so sorry. Have it. 0.33. And so we're looking at, okay, now I want you to know this isn't making sense to me, okay? Because I know that at 115, it's already a 1 Z-score. So it's a 1.33. Something's not adding up, right? I'm doing something wrong. I'm figuring that out. 120 minus 100 is 20, not 5, okay? And logically, this score is just not making sense. So I'm recognizing I'm doing something wrong in my math. So let's go ahead and erase this baby. And let's redo that. Oops, sorry. Okay, so let's go back and let's put that normal distribution back. Okay, and now let's look at, we're looking at X minus the mean divided by the standard deviation, which is going to be 120 minus 100 divided by 15 is 20 divided by 15. Now it's making more sense, right? If I do 20 divided by 15, it's going to be 20 divided by 15, it's going to be 1.33. That's making sense to me, okay? So my Z-score is 1.33. So now I need to go back and figure out what it's asking me because I forgot. It's asking me, what is the probability of randomly selecting an individual with a score less than 120, okay? So then if I go back to my whiteboard, it's asking me less than 120, okay? So what it's essentially asking me is over here, less than 120. So it's a percentage in the body. What percentage of scores are less than a Z of 1.33? And so that's gonna, I'm gonna now go to my unit normal table. And I'm gonna look up a Z-score of 1.33, which is right here. The percentage in the body is 90.82%, okay? 90.82%, okay? So lots and lots of practice built in. Hopefully that helps. You tell me, but I always like to draw a picture. So I feel like first thing to do is draw the picture. What is it asking? Draw a picture. I like to draw the picture first and then figure out what's it asking. Transform any X values into the Z-score. Determine which column you're going to use based on what it's asking. Locate the proportions or the percentages that correspond to that column, and then you can calculate your probability. Okay, convert it to the percentages. So here's a way in which you might use the unit normal table where we're saying, what's the probability of X falling between a 55 and a 65? And then it's telling me, given a certain mean and given a certain standard deviation. So given a mean of 58 and a mean of 10, I'm mapping this out and I'm asking, okay, first of all, I can actually find the Z-score that corresponds to 55 and 65. And what's it asking me? It's asking me for this percentage here. What is the probability that X is between these two boundaries? So this is a chance when I'm going to use that, that one D column where I'm looking at the probability or proportion of scores that fall between the mean and the z-score. And in this case, I'm going to look it up first for the mean and the z-score of 70, and then the mean and the z-score of negative 0.30. And I'm going to add those two together. And that's going to tell me the full probability in those two regions. And so we do that. We look up the negative 30, which is still 30, right? And then 70. And we're going to go ahead and look those up. So for 30, we're looking at this column right here, 11.79. And then we're looking at 70, and that's 25.80. And then we're going to add those together, and that's going to be about 37.59%. Okay. And that's what we get. Make sense? Okay, hopefully. Now let's look at probability, our number 2. Again, put me on pause and try to figure it out, but we're asking for what's a percentage of scores that fall between 65 and 75, and you're thinking, hold on, that's not the probability or the full tail because it's cutting this off. So there's a couple of ways that we can do it, right? We can first find the z-scores that correspond to these boundaries, and it's 0.7 and 0.170. What we can do is we can calculate the percentage between, using D column, between the mean and the 75 z-score, and then the mean between the D column for the percentage of scores between the mean and 65. And we can see that we can minus this out from this one, and that's a great way to do it, right? So the percentage of scores between the mean and 75, or 1.70 z-score, minus the distance between the mean and 0.65, or 0.70 z-score. So we first need to find those probabilities of 0.70 and 1.70. Oops, wrong one, sorry. So 0.70 is 0.2580. And what was the other one that we needed to look up? I should have written it down, I'm sorry. 1.70. Okay, so 1 now. I'm going to look up this 0.45. So it's going to be 0.4554 minus 0.2580 equals 1.97 or 0.1974, which is 19.74%. Okay, and let's go back and just make sure I'm right. I can make mistakes, right? Here we go, 19.75%. Okay, so you have to figure out what it's asking you. Use your picture to sort through that, okay? We can also look at finding X values that correspond to specific proportions and probabilities. So I look at the proportion for the z-score, and then I transform that back to that raw score value, okay? So again, use your picture. Instead of going from the raw score to the z-score, you're going from the z-score to the raw score, same diff, okay? And so here's the question: what is the commuting time for the 90th percentile? Okay, this should really be 90th percentile. And so it's basically saying when there's only 10% in the tail. And so I can look up the z-score that corresponds to 10% in the tail or 90% in the body, which if you look at that, okay, so 10% in the tail or 90% in the body is going to be right about here, okay? And then I now need to plug that back in. That's our z-score. Now I need to plug that back into our formula to calculate the raw score that corresponds to a z-score of 1.28. So I plug it back into my formula based on the mean of 24.3 and the standard deviation of 10. And I'm going to get an x value of 37.1. So 37.1, you're going to find that when it's asking me the commuting time for the 90th percentile is 37.1 minutes. Okay. Okay. So only 37.1, only 10% of the population drives longer than 37.1%. Okay. So let's see, what else is it going to go through? We can also look at finding a range of scores for X values. So what's the percentage of scores that fall between these boundaries, right? Go through the same motions. So again, this bottom line is corresponding to percentile, where 50th percentile, if you're scoring here or above, you're scoring above 50% of the population. Here, you're scoring above 84.1% of the population, so you're in the 84th percentile, okay? And then as we're starting to think ahead for what does this mean for inferential statistics, it really goes back to linking the probability with what's kind of the norm versus what's that critical region. So we're focusing on what is, we've talked in general numbers about beyond a z-score of 2. Precisely if we're looking at a 5% probability, when we look at the unit normal table, a 5% probability dividing it on both sides, so 5% divided by 2 is 2.5% in the tail. And when we look up 2.5% in the tail, that's going to be here, we're actually looking at a 1.96 z-score. So ultimately, we're establishing a critical region that corresponds to less than 5% probability. And what that means is we're looking for scores that are above 1.96 or below negative 1.96. Anything with a z-score beyond those boundaries is in the critical region, which it's said to be significantly different from the rest of the 95% of the sample. Now I'm just going to plant some seeds for you before we leave today's lecture, and this will be helpful coming up for the next chapter, okay? But when we're talking about inferential statistics, okay, and we're drawing a boundary here of negative 1.96 and positive 1.96, and what we're saying is anything above 1.96 or below 1.96 is in what we call the critical region. Okay, I'm going to throw some terminology. I'm just going to plant some seeds. If it's in the critical region, we reject the null. It's said to be statistically significant. Okay, and that's either here, so this is going to be, and it's a less than 0.5% chance of getting it. So P is less than 0.05, it's statistically significant, and we reject the null, okay? If it's not, and it's in this middle point, just like 95% of the population, then we fail to reject the null. It is not statistically significant. And it is greater than 0.05. The probability is greater. In fact, the probability is 95% that it'll fall in the middle instead of in the critical regions. okay? And what we're doing with inferential statistics is saying, is it in the critical region or is it not in the critical region? We get to decide what boundaries we're going to establish for the critical region. For the most part, we're going to operate on a probability of 5%. And so that's going to be z boundaries of negative 0.196 and positive 0.196. But we'll introduce you in the upcoming chapters to a one-tailed test or a two-tailed test, and we'll introduce you to alpha levels, which is the probability that we're going to set. And we can set a probability from 0.01%, 0.001%, or 0.05%. For the purposes of this class, I'll usually default to a 0.05%, but know that current research often uses 0.01% or lower. And we'll talk about what that all that means in the upcoming chapters. Right now, I'm just looking to help plant some seeds for you, okay? And so we are leading up to inferential statistics. We've learned about z-scores as a way to standardize scores. We've learned how those match up with probability in that unit normal table, and how we can calculate specific proportions and probabilities that correspond to each z-score. So now we can start to make predictions of scores based on our z-scores. We're going to now flip it, and we're going to talk, well, we're not going to flip it, we're going to build on it. We're going to talk about sampling distributions in the next chapter, and then we're going to use z-score for hypothesis testing. So a lot more to learn in this module. Have fun.